Okay, so hi everyone. So welcome back to this new video. So today in this video, we are going to learn about this question that goes by the name fix a tree, and it was asked in Codeforces round 363 div 1, and it is rated 1700. This problem will utilize the concept of functional graphs and cycle detection in a graph. So let us start reading the problem now. So the problem reads like this, that we are given a tree. A tree is an undirected connected graph without cycles. So the description of tree is written here. So let's consider a rooted undirected tree with n vertices numbered from 1 through n. There are many ways to represent such a tree. One way is to create an array with n integers where each p of I denotes a parent of vertex I. So here for convenience, a root is considered its own parent. So as you can see here, this is a rooted tree which is rooted at third node and three other nodes are present below it. So if we have to make an array for this rooted tree, then something like this can be made. That is, the parent of first node is 2 like this, the parent of second node is 3 like this, the parent of third node, that is the index 3, I'm considering one based indexing here. So the parent of third is third only, that is a self loop. And finally the parent of fourth node is 2, which is this. So that's why we can represent such a tree into this form of an array. Given a sequence from P1 to Pn, that is this whole array initially we will be given, one is able to restore a tree. So there must be exactly one index for which PR is equal to R. That is, if we have to make a tree as a rooted tree, then obviously in this whole array there could only be one element for which the parent will be itself. So the same thing is written here. And for all the other n-1 vertices, there is an edge between vertex I and vertex P of I. Let's read further. So a sequence from P1 to Pn is called a valid sequence if the described procedure generates some rooted tree or any rooted tree. So for example, for n is equal to 3 sequences, these are not valid. So you are given a sequence initially which may or may not be valid, and our task is to change the minimum number of elements in it in order to get a valid sequence. That is, to turn the original graph into a rooted tree. So print the minimum number of changes and an example of a valid sequence after that number of changes. And if there are many valid sequences achievable in the minimum number of changes, we can print any one of them. So in the input, first we have to take the number of vertices in the tree as the input. That can go up till 2 into 1 5. And the second line contains n integers from a1 to an, right? And in the output, in the first line we have to print the minimum number of changes that we have to do in order to get a valid sequence, that is a valid rooted tree. And in the second line we have to print any such array after doing the minimum number of changes to the given array. And if there are many such sequences, any of them will be accepted. So this is the problem statement, and here we are given with 4 examples. So let us now try to understand all of these examples one by one and see what this question is trying to tell and what logic we will apply. So let us now go to the blackboard. So this is the very first example given in the question. So in this example, the total number of nodes is 4, and this is the sequence that we have provided. So the first element is 2, the second element is 3, the third element is 3, and the fourth element is 4. So what we have to do is, as we have read in the question, that each of these elements in this sequence array corresponds to a node, and these indexes corresponding to these elements also correspond to the node. And also, if this 2 element is written on the first index, then it means that a edge is directed from the first node towards this second node. Similarly, if this 3 is written on the second index, then it means that a edge is directed from the second node towards this third node. Similarly, for this third index, it will mean that a edge is directed originating from 3 and going towards itself only, that is a self loop. Finally, for the fourth index, since it is equal to itself, so it means that a edge will direct from itself towards itself. So if you try to draw such a graph, then it will look something like, so the graph will look something like this, right? In this graph, if you remember, what was our task? So our task was to make some changes to this given sequence in order to turn this given graph into a rooted tree, right? So since we want to make a rooted tree, so we know that what a rooted tree look like. So in a rooted tree, there is a top node whose parent is no one. So you can imagine it like this is the parent of itself, and except this, every other node will be present below it. So something like this you can imagine, right? Since this graph given is disconnected initially, so somehow it also means that we have to connect these two different components into a single component, because in a rooted tree or a tree everything is connected, they are not disconnected, right? So what we have to make sure is that the whole graph should be a connected graph, and once connected we have to also ensure that since it will be a tree, so we know that in a tree there are no cycles, right? So there has to be no cycles in the rooted tree, so we also have to make sure this, and it should be connected also. Since in the question it was told that we have to do the minimum number of changes in order to make this condition possible, that is we have to change the minimum number of elements in this sequence array. So since in a rooted tree the top element will be the parent of itself, and for every other node there would be some different parent other than itself, right? So if we look carefully in this first example, that is this sequence, so for 3 the parent is 3, and for 4 also the parent is 4. That is, initially what is the condition? The condition is that both of these nodes are acting as the root node, but we just want one root node and not two. So initially two different root nodes are present, so we just want one which will be a parent of itself. So this is the very first observation. So we have to decide out of which 3 and 4 we want to make the root node. So suppose I decided to make this third node as the root node. So if I make this third node as the root node, so it means that I have to change this fourth node from root node to some other node, right? That is, cannot point to itself anymore, because if it points to itself then it will be considered as root node, and in that case we will be having two different root nodes. But we don't want that. Since we want a rooted tree, so there can only be one root node at the top. So what we can do is, since I have told you that this 4 cannot point to itself, that is we have to change this element now, because earlier 4 was pointing to 4. So now we want a different element value at this position, and once we update this position to a new value, I can say that the total number of changes I have done is +1. So if I direct this edge, that is this edge which was initially pointing to itself, let's say it points to some other node. If I draw it even more better, so initially this was given, right? And I told you that this 4 cannot point to itself anymore. So now this 4 can either point to this 1, or it can either point to this 2, or it can either point to this 3. So if I decided to make this 4, let's say it points to 2 now. So something like this you can imagine. So if it points to 2, then it means that the parent of 4 will become 2, right? So in that case I have to write 2 here. So let's say I write here 2, and after writing this 2, I can surely direct this edge here like this. And now if you see, then this whole tree is now a rooted tree. Why? Because we have connected the initial two disconnected components into a single component now, and there are no cycles present in this. Now some of you will think that this is a cycle because 3 is doing a self loop, but we are allowed to do this because in the question, if you have read, then it was told that in the final array only one element has to be a parent of itself, which will be the root node. So that's why we will not eliminate this in any case. This will remain. But except this root node having a self loop, any other node in the part of the tree cannot have a cycle, because if it has a cycle, then it will not be called as a tree anymore, right? Because a tree has no cycles. And also if you remember the condition of tree, then it should have n nodes and n-1 edges. So since here the total number of nodes is 4, so there has to be 3 edges, right? So this is the first edge, this is the second edge, and this is the third edge. So you don't have to consider this as an edge or as a cycle or anything. It is just present virtually in the array, something like that. So now since both of our conditions are satisfied, so that's why we will now print the total number of operations it took us to do this. So can you tell me what is the total number of operations it took me to do this? Just one, because I just changed one element in this whole array in order to turn the initial given tree into a rooted tree, right? So that's why I will print 1, and after printing 1 in the new line I also have to print this array, right? So that's why I will print 2 space 3 space 3 or space 2. So this is a one valid answer. I have directed this fourth node towards this second node. If I had directed this fourth node towards this third node, then also I would have got a valid tree, or a valid rooted tree rather. Similarly, if I have directed this fourth node towards this one node, then also I can say that I would have got a valid tree. And for those corresponding cases, I have to write the element here accordingly, and thereby in the final answer as well. So if you look in the output of the given example, so the expected output was, so the expected output written in the problem statement was 2344. So if it has to be 2344, then it means that since initially we were given 2334 and now the expected output was 2344, then the only element that has been changed here is this, right? That is, it has been changed from 3 to 4. So if we had done that instead of this would have remained 4, and instead what we could have done is we could have changed this element to 4. And if we had done this, then it means that edge which was earlier pointing from third node towards third node, that is this node, will have been erased, and instead of this a new directed edge will be present from the third node towards the fourth node, right? So something like this. So this is also a valid rooted tree because, and everything is connected also. So for this we could have printed 1 and in the next line 2344, which is the given output also in the example. So I hope you understood this thing very well. Let us now move to the second example. So this is the second example given in the question, and in this example 5 nodes are present and this is the given sequence. So if we had to direct the edges, then we can do it in the following way. So since this is the indexing here in one based, our edge is directed from first node to the third node for the first index. Second, our edge is directed originating from 2 and going to itself, that is a self loop like this, and then from 3 to 2 like this, and then from 4 towards 5. So from 4 towards 5 and then from 5 towards 3. So since we have to draw it from 5 towards 3, so you can imagine it something like this. So from 5 towards 3 like this. So if I had to draw it properly, then so this given sequence will finally look like this. And if you remember, then what was our task? Our task was to make the whole graph connected plus remove every other cycle present. So as you can see that in this graph, it is already connected first of all, and also other than this root node here which is directed to itself, in the whole other part of the tree there are no cycles, right? So you can look in this sequence array also that for this second index only the value of element is equal to the index, which means that there is only one node which has a potential of becoming the root node here. And since there are no cycles present in this graph and everything is connected already and just one root node is present, so that's why I can say the total number of minimum changes that we have to do is simply 0. So that's why we'll print 0. Whatever given in the input we will just print it simply because we have done no changes in that array. So 3 space 2 space 2 space 5 and space 3. So this will be our answer for this second example. So this is the third example given in the question. So for this example a total of 8 nodes are present, that is from 1 to 8. So if we had to direct the edges, so let's do it one by one. So first we will direct a edge from 1 towards 2, that is the parent of 1 is 2, then the parent of 2 will be 3, then the parent of 3 will be 5, then the parent of 4 will just be 4, then the parent of 5 will be 1, then the parent of 6 will just be 6, then the parent of 7 will be 6, so something like this, and then finally the parent of 8 will be 7, so something like this you can imagine. So now if you see in the sequence array, then there are a total of 2 elements for which the value of index is equal to the value of element. So that first node is this 4th node which is directed to itself, and then second this is the 6th node which is directed to itself. So a total of 2 nodes are already directed towards itself like this. What was our goal? Our goal was to make the whole graph connected, because in a rooted tree everything is connected and not disconnected. So since initially it is disconnected, so we have to make everything connected, and also you have to make sure that there are no cycles at the end. And if you have noticed, then I have done a small mistake, not a mistake actually. Here first I have started from 1 and then again I have written 1 here, so it should be something like this, that is a back edge, right? So let me do that here. So instead of directing it there, it is like this only. So that's why, since there are only 2 indexes here for which the value of node is equal to the index, so that's why we can say that only 2 possible nodes can be considered as the root node, right? And since in a rooted tree only 1 root node is present, so out of this 4 and 6 we have to decide to what node we have to make a root node. That is, to what node the value of index will be equal to the element. So suppose we have decided to make this 4th node as the root node. So if we have decided to make this 4th node as a root node, then the value at the 4th index will remain 4. It will not change. But the value that was before present on the 6th index, that is 6, will no longer be 6, right? So now we have to change this value. That is, we have to direct this edge somewhere else now. So suppose we have decided to direct this edge from this 6 towards this 4 now. Then we have to write 4 here. And now these 2 components are connected. Similarly, things will now get interesting. Now this is a rooted tree in itself, and this is a cycle. And by now we have already done 1 changes in total. That is plus 1 changes, right? But since these 2 components are disconnected and we have to connect them, so it means that somehow we have to direct a edge present in this cycle or this component towards any node of this rooted tree, right? So suppose I have decided in this cyclic part of this component, I have decided to direct this back edge from 5 to 1, which is creating a cycle, because we know that in the rooted tree we cannot have cycles also, right? So since we cannot have cycles, that means we have to remove this connection, that is from 5 to 1 we have to remove. And it also means that since we have to remove it from 5 towards 1, so we have to also remove this and change this element to something other. So now if I have done this, then it means that I have to direct this 5 somewhere else now. So now where I will direct this 5? So let's say if I direct this 5 now to any node of this component, let's say I direct it towards 6 now. So what will happen? So if I direct it something like this, the whole thing now will become a rooted tree successfully, because everything is connected, plus there are no cycles anymore, right? So this is the root node and everything present below it is connected and has no cycles. So that's why I will write 6 here now. And in order to do this thing, since the minimum number of changes that we required is 2, so that's why I will just print a 2 here. So I will print a 2, and after printing this 2, we also have to print this array. So that's why I will print 2, 3, 5, 4, 6, 4, 6, 7, something like this, and then this will be considered as a valid answer. So I hope you understood about all these 3 examples what the question is trying us to print. And if you have noticed one thing, then since we were always given initial graph in the form of an array such that we have to direct it from the index towards the node, so it means that from any given initial node there will just be one outgoing edge, right? So there will just be one outgoing edge every time. So it is possible that towards a node multiple edges will be coming, but from a edge only one edge will go out. So more than 2 or 2 will never go out. Only one edge will always go out. And since this is the thing, then we can say that the initial given graph can be called as a functional graph, because this is the definition of functional graph, that only one outgoing edge should be present from each node. So the given graphs are functional graph completely, right? This is just one important observation that I thought to tell you. And there is a dedicated algorithm in order to detect cycles in the functional graphs, which is called as Floyd's algorithm. So if I show you, then a dedicated blog is written here on the USACO website, as you can read, that what is functional graph actually and how Floyd's algorithm helps in order to detect the cycles in this functional graph in O of n time and O of 1 memory, right? So you can read these things if you want, but I think we will not be needing the Floyd's algorithm here. Instead, a simple DFS will work in our case. So now, what is our goal exactly? So our goal is very simple. Whatever the initial sequence will be given with, we will make a directed graph out of that array, right? So that graph might either be connected completely or can be disconnected initially. So if it is disconnected, then our goal was to make this graph into a rooted tree, right? And we know the definition for a rooted tree is very simple, that no cycle should be present at all, plus everything has to be connected, right? Everything has to be connected for a rooted tree. So you have to make sure these things. And since in a rooted tree, the top element that will act as the ultimate parent of the whole connected component will be the root. So that's why in that initial array, there could only be one element at the end for which the value of index will be equal to the sequence of that index, right? So we have to make sure this also. First, our work will be to check how many possible rooted nodes are present. That is, how many nodes are there that are directed to itself, because they will act as a potential candidate for a root node, right? So they can act as the root node. So if there is even one at least or more than one, then we have to select out of those rooted nodes a one root node that will act as the ultimate parent for that whole component, right? That is, it will be present at the top, and in the array the value of index will be equal to index for that root node, right? So first our work will be that. And suppose in the given graph originally that we have constructed through the given sequence, so in this graph, if there is no node which has a self loop like this, that is, which can act as a potential root candidate, then what we will do in that case? So we cannot left it untouched, right? We have to select some node that can act as the root node. Since we have to minimize the number of operations, so that's why we will select such a root node which is a part of a cycle. So if suppose the initial given graph was something like this, that is this, this is the first component and this is the second component. So if this graph is given initially divided into two components, since we have to convert this whole graph into a rooted tree, that is, value of index will have to be equal to index. So in the initial sequence for this graph, there will be no index for which the value will be equal to that index, right? So we have to choose one node. So that's why we will pick any node of a cycle that is creating a back edge and leading to a cycle. So suppose if I decided from this component through this cyclic path in order to choose a node which is creating a back edge and forming a cycle. Suppose earlier it was directed from A towards B, that is, the index was A and it was written for the element B, right? So now I will erase this, that is, it won't be B here anymore, and I will say that this will act now as the root node, right? This will now act as the root node, and if it acts as the root node, then I can say that this will be now A. And once the root node has been decided for the whole graph, then what I will do? My next task was to ensure that everything is connected and has no cycles. Since there is only one cycle remaining in this part, so if I suppose this was connected from C to D before, let's say. So earlier it was connected from C to D in the sequence, and if I decided to erase this edge, that is this D, that is the back edge which is forming a cycle, right, and direct it to any node of this component. Now let's say I direct it towards this node, and let's say the name of the node was X. So now this is X. So if I do it like this, then you can notice that since before doing this, this was forming a cycle and was not connected with this part. But as soon as I remove this edge from C to D towards C to X now, then this cycle is also removed successfully and the two components are also connected now. So that's why picking a back edge from each cycle and connecting it to a different component will always be feasible, because it will always help us by applying the minimum number of operations in order to create the whole graph as a rooted tree. Because here if you see, then we just applied two operations. First we change the direction from A to B towards A itself, so that we have decided a route, because earlier there was no such node. And then we decided to direct from the C to D towards now C to X, and in this way the whole graph is now turned into a rooted tree, because everything is connected and just one rooted node is present and has no cycles at all. So since only two operations was required to do this, so that's why we will print 2 here, and whatever the sequence will be there, so that sequence. So that's why in the given sequence we will always check that if there is any node for which the value of index is equal to itself. So if it is there, then it means that we don't have to direct this explicitly by ourselves, and it will save one operation, right? But if there is no such node, then it means that we have to select one such node that can act as a root node, and that will cost us one operation at least, right? And after doing this, we have to make sure that whatever the cycles are present in the remaining graph, we have to decyclize it. That is, we have to remove all the cycles and direct the edges to the different component. And if some of you is confused that to what node exactly we will direct this node, because here I have directed it towards X, but since I told you that you can direct it in any node of this component, so that's why what we will do instead is whatever back edge we have to direct, we will always direct it towards the root only, because even if I do this, that is from C towards A, so it won't be X anymore, it will be A in every case. Then also the whole tree will be a rooted tree only, as you can see, right? So that's why we will always direct this back edge towards the rooted tree for every cycle, and that will every time help. I think I have told you everything in very detail. Let's now move to the coding part to see how it will look in the code. So let us now go to the code editor. First we have to take the inputs for the total number of nodes, that is n, and then we have to take the inputs for the sequence. So let's do it in one based indexing only. Let me declare this array here outside, and since I have used one based indexing and the total number of nodes that can have here is 2 into 25, so let me declare a const here. So this, let's keep it as max n here only. So once the sequence is declared, I will take the input here like this, that is this. Since we know that we have to direct a graph from this I towards this sequence of I, so let's create an adjacency list here for the same, and it will also be of one based indexing only like this. So here I will say that g of I dot push back this sequence of I like this. And once this is done, that is the input for the graph has been taken. What I told you that we will check first, or rather we will fill an array consisting of each member of all the cycles, because even if it is a self loop node, then it will still be present in that, because it will be considered as a cycle, right? So in order to do this, let's do a simple DFS call for all the nodes, because the graph might be present in disconnected components as we saw. So we will do it from 1 towards the end like this, and we will check if this node is still not visited as of now, then we will run a DFS starting from this I. So let us declare the visited array also here. So if I write the DFS function here, then I am passing the node only here, right? And as soon as we enter, then we know how to detect a cycle using DFS for a directed graph. So we use the concept of visited and path visited, right? So that's why I also have to declare another array, that is a path visited array like this. So as soon as we enter the DFS call, first we will mark this node as visited, and also we will mark this node as path visited, and then we will iterate through each of the neighbors like this, and then I will check if this child is not visited as of now, then I will call the DFS, and if somehow this DFS call returns true in future, that is a cycle is detected, then I will return a true. So if this DFS of child returns a true, I will return a true. But if this is not the case, that is, it is not visited. But if it is path visited somehow, then it means that this edge now from node to this C is now acting as the back edge, right? And since it is acting as the back edge, and sorry, I think I should keep it as bool rather than this void, right? So yes, if it is path visited, then what I am saying is this node to this child is a back edge, and if it is a back edge, then it means that we have detected a cycle and we can return true. And before returning that, we can store this node that is originating that is creating the back edge in some vector. So let us declare a vector for the same, and let's name it as heads because it will be containing one member from each cycle. So I will say heads dot push back this C, or rather this node, right? And we know that after doing this, what we used to do, we just used to mark the path visited of this node as 0 and return false. But if we do this, then there is an issue, because since we know that in a component multiple cycles can be present, so that's why in this question it is not important for us to check if a cycle is present or not. It is more important for us rather to check all the cycles. So that's why we will not return one immediately after detecting a cycle. Rather than we will keep it exploring for every other cycle if present, because we need to remove the back edge from every cycle. So that's why every member of each cycle, so that's why one member from each cycle must be present in this heads array, and that's why we will remove that return one. So once we have written this, so now in the heads array we have all the possible members. Let's say the root is -1, and I will iterate through every head that I have just collected, right? And if there is some head or a node in the original graph which is pointing to itself, then we know that in the sequence array the value of C will be equal to, that is this child will be equal to the sequence of C, right? So we will check the same thing. If this C is equal to sequence of C, then it means that this node can act as a possible root node without requiring any one extra operation. So I will say that root will be this child, and then I will just simply break from this. But if I just check after it that if my root is still -1, then it means that we have never got a node which is pointing to itself in the original graph. So we have to choose it explicitly now, and that will increase the total number of operations. So that's why if I say that the total number of operations initially is 0, then it means that the number of operations now will surely increase by 1, right? And also, since we know that we have to choose a root node now out of any nodes present in this heads array, so let's say we choose heads of 0 as the root node because we can choose any, right? So let's say we choose this, and if we choose this, then it means that we have done one change in the element of the original given sequence. That is, now we have to set this sequence of root as the root, right? And the number of operations is increased by 1 for sure. And after doing this, what is our next task? Our next task is to direct all the back edges of every other cycle towards this root node, right? So that's why I will again explore this heads array and check if this C is not equal to root, because right now the root might have changed to this instead of this, right? So if this is not the case, that is the child of this head array is not a root, which means that this is a back edge, right? So this, which means that this C is a part of cycle as of now and is forming a back edge, right? So we have to redirect it towards the root. That is, we have to set the parent of this C as the root. So that's why I will say the sequence of this C will be root now, and in doing this the number of operations will surely increase by 1, right? Because what would have happened if this would be equal to root? So if this would be equal to root, then we would have simply set sequence of root equal to root, so nothing could have changed in that case. But the total number of operations will again have been increased by 1, which is not true because we have already increased it here. So that's why we'll get a wrong answer in that case, and that's why it is important to give this check. And once it is calculated, we can say that the final number of operations that is required is this, and in the next line we have to print this sequence array. So I will just print it manually like this from 1 to n. And at last just return. So now I think I have written the complete code here. So I think I have found a mistake here. So this will not be C, this will rather be sequence of C. And also one more error here that I have done. So it would be double equal to, because I am comparing it, right? So now if I run it, I think we are getting the correct answers. So since outputs might vary, so this is not an issue here. So now if I submit it onto the platform, let's see if we are correct or not. So as you can see that our solution is accepted now. So this is the whole code that we just wrote, right? And I explained you each and everything in very detail, what is the logic behind all this. So thank you so much for watching this video till this point. If you are new, please consider liking the video and subscribing the channel, because there is a lot of amazing and professional content here related to graph theory and segment tree. And if you have any suggestions, you can write in the comment section. I will read your comments and see what possible improvements could be made. And please like the video and subscribe the channel, because we are close to 500 subs. So yeah, thank you so much for watching these videos. Thank you.